And what is the strategy that we propose? So we do spectral element in space using Lagrange basis with FEKT point sets. We are in continuous Galerkin setting. We use high order scheme in time, BDF and eventually algebraic factorization methods. And we would like to, and the coupling between the structure, basically we have high order mesh, so we will see that it doesn't work at the moment. Regarding the interface operators, we do nodal projection, and for the full problem at the moment we do only fixed point, which is rather crude. But now we are working on a semi-implicit scheme which was proposed by Gerbeau, Grandmont and Fernandez. And in the fixed point iteration we use Aitken relaxation. So the algorithm reads like this, and basically with all the tools that we developed before and some extra ones that I have not shown here, basically you have exactly about the same amount of lines of code for this algorithm in C++. So this is really implemented like with one-liners like this in the code. So here we just, at each time step we extrapolate the structure displacement here, then we do the fixed point iteration for the fixed structure coupling. We compute, given the displacement, we compute the ALE map and the computational domain. We solve for Navier-Stokes, we compute the normal stress, the structure, then we compute the structure displacement, and then we check here for tolerance, and we apply the Aitken relaxation. So here are some of the one result here. So we have a pressure wave coming from the left to the right. So it's BDF3 for the fluid, P2, P4 elements. The H is 0,2, delta T 10-6. There are no stabilization, and we use BDF3 for the structure and P1 elements for the space discretization. So you see the pressure waves going through, and here are, so this is very recent results, and here are some properties that have just been gathered. Yeah, I'm done. So on this graph you have the time step, you have the time, sorry, and here you have the average number of iteration. And when we increase the order approximation, it doesn't change the number. This is the average number of iteration for the fixed point. So here, when we increase the order for the Fritz solver, it doesn't change the fixed point iteration. But now, if we look at the structure, if we increase the order for the structure and we keep the geometry order to 1, then it still converges. But when we go to higher order geometry, at the moment, the fixed point iteration they don't converge. So also that we expect that with a semi-implicit scheme, we might have some good result. But at the moment, the fixed point doesn't do its job. Also, what is interesting is that if you fix the fluid BDF order and you increase the structure BDF, then you decrease the number of fixed point iteration, and the average fixed point iteration. This is summarized on this slide here. You have two ways of looking at this slide. Either you look at just one block here. So this is BDF1 structure, BDF1, BDF2 structure, BDF3, BDF4. So if you have BDF1 for the fluid. So we have BDF1 for the fluid, and you look at the average number of iteration for the structure. And you see that when you increase the BDF for the structure, you decrease the number of fixed point iteration. And the same here. On the other hand, if you look at it that way, so what you do is that you increase the BDF for the fluid and you fix the BDF for the structure. So for example, we look at the red rectangle here. then each time the number of iteration, average number of iteration increases. And here we have no green part, which means that the fixed point actually didn't converge. So for BDF1, for the structure here, it didn't converge. Yeah, so these are next steps. Well, I'm going to skip that. Okay, so just to finish some ongoing and future work that we are things that we are doing. So regarding life, the core development, we are working with IFP on a new, more general mathematical framework that would allow us to include finite volume, mimetic, finite difference method. I mean, a very wide range of methods. Basically, you will be able to reuse the entire language. We need some new elementary operators, which are not available at the moment, but basically, it will be very easy to extend life to this framework. This is work from the mathematical side by Robert Aymar, Daniele Di Pietro, Alexandre Hern in France. At the moment, we do manual differentiation when we have a nonlinear problem, and we like to extend it to automatic differentiation, computing the Jacobian automatically. Full parallelization and domain decomposition framework. At the moment, we don't do domain decomposition. We do just partition of data. And we are working now on exploiting hybrid architecture, so typically cell architecture, IBM cell or CPU, GPU machines. And well, this is not exhaustive. Huh? And regarding application, well, we are working on this at the moment. We go to 3D, and we would like to do blood flow rheology, and we start also a work with IFP on CO2 storage simulation. Yeah, that's it. Thank you.